Okay, welcome back. Now you read the problem, you think about it, you try to solve it by yourself, and you come back. So, what it says, you are in Mars, a planet, a different planet than the Earth, where the acceleration A is 0.379 g of the g is the acceleration of the Earth, 10 meters per second squared, so will produce an acceleration. So the acceleration in Mars is 3.79 meters per second squared. So it says that the times to come back, when you launch something, the time to come back is 8.5 seconds. 8.5 seconds means that the time to go up is 4.25 seconds. So what it's asking you is, don't read what it's asking you. Write the equation of motion. The equation of motion is v of t is an equation of motion with constant acceleration. It will be v of t equal v0 plus at, y of t equal y0 plus v0 t plus 1/2 at squared. So we plug in the numbers for this particular case, where the acceleration is minus 3.79, and here is v0 at minus, sorry, I made a mistake, 3.79 divided by 2. So you have to correct the mistake, 3.79 divided by 2. So once that you wrote the equation, you read the problem. So the equation says that v of t is v0 minus 3.79t, and y of t equal y0, but you launch from the floor. So y0 equals 0 plus v0 t. These are the two equations. So the first thing that I'm going to try to do is, when the time t is 4.25, the final velocity is 0. So this will allow me to find the time to go up to the maximum height. So if I do it, I will find that the maximum height is v0 equals 16.10 meters per second. Perfect. Now, if I take the second equation and I plug in y at this time, I will find v0, 16.10, v0 by t, the time elapsed, 4.27, minus 3.79 divided by 2. 3.79 divided by 2 is, let me do it, 3.79 divided by 2 is 1.9, approximately 1.9, so this is 1.9 by t squared, multiplied by t squared. So 16 by 4.25 is 68. And this is 1.9 multiplied by 4.25, multiply again by 4.25, is 34.22. 34.22, let me erase here. So it will be minus 34.22. The height at this position, at this time, 4.25 seconds, it will be 68 minus 34. It will be 34. Oh, 34.70 meters. So the maximum height is 34.70, and the problem is solved. Let's go to the next one. Please read the problem carefully, try to solve it by yourself, and come back. So read this problem, try to do it by yourself, and come back. So this is an interesting problem that you should pay attention to know how to solve it, because it involves the manipulation of the equation in, in a very, very nice way. So the idea is like this. You are at the Earth, and you launch something from the floor from y0 equals 0. You launch something, an object, with velocity v0. We know, and we did in class, that the object will decrease its velocity because the acceleration is minus 10 meters per second squared. The object will go with the velocity decreasing because the acceleration is negative. Is producing a change in the velocity. The acceleration is the change in velocity, so it produces minus a change in velocity of minus 10 meters per second every second. So the velocity will. So what will be the equation for constant acceleration? The equation for constant acceleration is that v final equal v0 plus it, and y final equal y0 plus v0 t plus 1/2 t squared. We write this equation for this particular case. What we want to do is it's if the object arrives 12 meters up from the floor, 12 meters, and you do the same thing, you do with this acceleration in the Earth, and you launch again the object on the moon with the same velocity, what will happen? What are the differences? And the differences are that the equation will behave different because the acceleration will be different. Instead of minus 10, the acceleration will be 1.7 meters per second squared, because the acceleration is, say, 0.17 g, and g is 10, so it will be 1.7. Of course, the acceleration is negative. It's negative according to how we took the system of reference. So, for this experiment, when we launch with velocity v0 and arrive to the point 12 meters, what is the initial velocity? Okay, we solve it. V final equal V initial minus acceleration t 10 by t. When the velocity final is 0, the time t is v0 divided by 10. So we don't know t and we don't know v0, but we know the relation between t and v0. I will plug in this t into the equation of y. What is the equation for y? y0 is 0, so it will be, and y will be 12. So the equation, this equation, will be 12 equal v0, that I don't know, by t, but the time t is this amount, is v0 divided by 10. So I will plug in v0 divided by 10 instead of t. So v0 multiplied by t, well, let's go to write the equation, minus 5 t squared. So 12 equals v0 by t. v0 divided by 10 minus 5 by t squared. T squared is v0 squared divided by 100. Okay, so I have this equation. So what I have to do now is to solve for v0. If you do it, you will find it's here, it's down, it's here, it's here, it's here, it's here, it's down here, that the velocity, the initial velocity, is 15.5 meters per second. So the time elapsed for the object to go to the maximum height, in this case, t, is v0 divided by 10, by the acceleration. So it's 15.5 divided by 10, so the time elapsed to go to the maximum height is 1.5 seconds. Perfect. Now we do the same experiment in the Earth, in the Moon. We launch the same object at 15.5 meters per second in the Moon, where the acceleration is minus 1.7 meters per second squared. So this means that the Moon produced change in velocity of 1.7 meters per second in every second. So it decreased the velocity because of the minus sign. So what are the equations in the moon? That the velocity is v0 plus it is the equation for a motion with constant acceleration. What is y of t? The same equation for constant acceleration that we have studied. So what it is in our case, it will be vt equal v0, 15.5. That the problem is assuming that we are launching the object 15.5 minus a, but a in this case is minus 1.7 t. And y equal y0, 0 plus v0, 15.5 by t, minus 1.7 divided by 2 by t squared. As I said, wherever you find this kind of problem, write the equation of motions, and the equation of motion will take you to the solution. So in this case, it's asking you how long he will arrive up. So indeed, it's not asking you how long it arrive up, how long it will take to go up and down. So the time t to arrive up to the maximum height is when the velocity in the moon is 0. So I will have this equation, I will plug in v equals 0, and I will obtain the time. The time is 9.11. Compared to 1.5, the difference in times is, well, 9.11 minus 1.5. But I think that this is how longer to go up. So 9.1 minus 1.5 is 8, 7.61, right? 7.61 seconds. But I think that the problem will say coming back to the floor. So this time will have to be multiplied by 2. It will delay the same time to go up than to go downwards from the maximum height. And the problem is done.